Today's problem was submitted by a viewer, and it says, a sequence of rooted trees, Tn, is constructed such that Tn has n nodes numbered 1 to n. The sequence starts at T1, a tree with a single node, as a root with the number 1. For n greater than 1, Tn is constructed from Tn minus 1 using the following procedure. Trace a path from the root of Tn minus 1 to a leaf by following the largest numbered child at each node. Remove all edges along the traced path, disconnecting all nodes along it from their parents. Connect all orphan nodes directly to a new node numbered n, which becomes the root of Tn. Okay, so that's kind of confusing, but there is an example given here, a diagram, which I'll try and copy so that you can see. For example, the following figure shows T6 and T7. The path traced through T6 during the construction of T7 is colored red. Okay, so you trace the path, remove all the edges along the traced path, connect all orphan nodes directly to a new node numbered n. Okay, so you kind of rejuggle the tree. All right. Let f and k be the sum of the node numbers along the path connecting the root of Tn to the node k, including the root and the node k. For example, f6,1 is 6 plus 5 plus 1 equals 12, and f10,3 is equal to 29. Okay, find a formula or algorithm for the function f and k. Okay, and I'm given by the viewer a few more of the results. So I'm given f10,7, f30,21, I'm given a bunch of results so that I can check my answer. Now I'm also told in a message from the viewer that this problem could take anywhere from 30 minutes to a few hours to solve, and it comes from a website called Project Euler. I've done a large number of Project Euler problems a long time ago, but never made it up as high as problem 872. And I happen to know that these problems can often take a lot of time and thought. So I'm not sure if I'll be able to figure this one out in one sitting. I might have to spend some time thinking about this on my own and return to it. So the first thing I'm going to do is to try and get a better understanding of how these trees are constructed. We of course start with a tree that has simply, that's T1. Okay. T2 is simply going to be, of course, 2 connected to 1. Okay, T3. Okay, so trace a path and remove it. So the first thing we do is we remove like that. And then connect all the orphaned nodes to another node. So T3 becomes this. Okay, so let's make T4. So the first thing we do is we take the original tree, go to take a path to the highest node, so we delete that. And then we pop in the number 4 and we connect like that. Okay, so T5 So, oops. We're going to start with that tree. I trace down a path going to the highest numbered child. We delete those paths and then connect like this. And to make T6, I hope I end up with the same tree given here to make T6. So we start at the root, which is 5. We go to the highest child, which is 4, and then 2. We delete those paths, and we connect those to the number 6. Okay, so let me compare this to the example tree as given. So 6 should connect to 2, 4, and 5. It does. And then 5 connects to 3 and 1. Okay, so I'm constructing these trees according to the algorithm correctly. But then f and k, the function we're asked to compute, is the sum of the node numbers connecting the root to the node labeled k. So for example, let's say f6 comma 3 would be 6 plus 5 plus 3. Huh. I mean, like, there's no way I'm going to be able to figure this out in one sitting. This is going to be the kind of thing I would have to sit and think about in silence for a long time. And I feel like, you know, from like a coding perspective, Project Euler problems typically revolve around writing code to solve problems. From a coding perspective, it seems like you basically want to choose, you want to sort of somehow keep track, you know, for f6.3, you want to find this node 3 and sort of keep track of what happens to its parents as you construct. Or maybe there's like a recursive relation. Like, maybe there's a recursive relation for f and k in terms of f n minus 1 k. You know, some dependence on that. I mean, I don't mean specifically it's just going to be a function of this number. I mean, there's going to be some way of there's probably some way, by understanding the algorithm for constructing these trees, how to keep track of this sum we're trying to compute by knowing like what the children of each node are. The thing that's weird is a number can lose its child. So like here, and going from T4 to T5, 3 has a child of 1, but in the next tree you lose, 3 loses its child. I mean, yeah, I'm not going to continue trying to figure this out in a live video in this exact sitting. But some things I might try and think about on my own while not recording are like, you know, if I'm trying to compute f6.3 in some kind of closed form, like without actually constructing the whole tree, you know, once I have T3, for example, is it important for me to keep track of the children of 3 as things move, or what the parent of 3 is? I mean, well, we don't need the children of 3 ever. The sum is, it's the sum from the root of the tree down. So like, for example, f of 6 comma 5, it's 11 because it's 6 plus 5. That's the sum of the numbers down there. So at any point, you need to keep track. You're basically computing the path. This function is computing the path from node 5 all the way back up to the root of the tree. So I don't know if this is a general pattern, but something that I notice is that, you know, so it's a given that n minus 1 will always be a child of n. And then the children of this one are always odd. You know, so like, if I look at the second level of the tree, all descendants have the same parity. 6 has even children, 5 has an odd child, 7 has only odd descendants, 6 has an even descendant. These are all even, these are odd, these are all odd, that's even. I don't know if that'll stay in general. I'm gonna maybe spend more time thinking about this on my own at some point. There's no way I'm gonna figure this out live during a recording in an amount of time that's reasonable to post as a video. So I'll come back to this one, and if I ever do have some thoughts, I'll come back and continue this recording. Okay, so I'm returning to this problem after being able to think about it for a couple of days. And I have some ideas that I'd like to pursue. And one of them in particular, I'm pretty confident will lead us to the right answer. A lot of what I did relies on implementing some things numerically and looking for some patterns. And then I'm going to basically just abuse those patterns to try and compute this function explicitly. I might not be able to write down a closed form value expression for this function, but I'll definitely be able to write code or an algorithm that should execute it extremely quickly for arbitrary values of n and k. So after my first segment of recording, I really thought that I wouldn't be able to make progress on this, and I sent an email to the person who submitted this to say, don't get your hopes up that I'll make much progress. They responded with a hint. I haven't actually read that hint yet. So what I'm going to do is try and explore some of the numerical stuff that I've done first. And if that doesn't end up getting to the right answer, then I will read the hint and see if there's something more that I can do. Okay, so the first thing that I did, just to sort of get a feel for what is going on in this problem, is I wrote some code that generates the trees according to the recursive relations given in the problem for an arbitrary value of n. So what I'm going to do is I'm going to show what the output of that code looks like, and we'll compare it to the trees T9 and T10. Here is the code itself on the left. I'm not actually going to go into any detail on what this does. It's just implementing exactly the rules that were given. And I'm not using an actual tree data structure to store things. All I'm doing is I'm going to declare some arrays which will store for each node in the tree, it's going to store what the corresponding parent of that node is. And that's enough information to completely reconstruct the trees. And not only that, it's a really easy way, if you have this array, it's very easy to then evaluate the function for a fixed value of n for any value of k. So let's look at this array first. All parents, I'm calling this all parents 9. Okay, so this is all the information we need to compute or to reconstruct the tree T9. If we compare it to what I have written here, done by hand, let me explain what's going on here. Okay, so the first element in this array is 9. That's to indicate that the parent of number 1 is 9. Okay, so 1 is connected to 9. If I look at, for example, 1, 2, 3, 4, the fifth element of this array, which is also a 9, we see that the parent of number 5 is the number 9. If I look at the sixth element of this array, 8, that means that the parent of 6 is the number 8. So T9 is an array. Well, it can be stored in an array with only 8 elements. Of course, I don't need the parent for the number 9 itself, because in T9, the number 9 doesn't have a parent. Okay, I can do this also for tree 10. And if I look, for example, at the third element in this array, that's a 7. That's saying that the parent of the number 3 is the number 7. Take any other arbitrary one. So this is the fifth element of that array. It's saying that the parent of 5 is the number 9. Okay, so how would I use this array to then easily compute the function fnk? Okay, so let's say, for example, I want to do this. I want to compute f10.5, this quantity as dictated by the question. Well, what I would do, I take this array. Well, let's talk about how we would do that in the tree itself. We start here and we go up to the 9, and then we go up to the 10, and we just add all these numbers together. And that would give us f10, 5. Okay, using the array, what I do is I start with the number 5, then I look at the fifth element of this array, which is 9, and I add a 9, and then I use this number 9 as the new index, and so the ninth element of this array is 10, and I add the number 10. Okay, so basically, starting at the value of k, you look at the kth element of this array, whatever that number is, you replace the index with that number, and you look for that element in the array, and so on, and you just sort of work your way up. Okay, so I have a very small piece of code which also implements that. Here, if I give an arbitrary value of n and k, let's go 10 and 5. So if I run this, it tells me that the answer is 24. And if I look at 5 plus 9 plus 10, that's 24. Okay. The person who submitted this question to me gave some other values of n and k that I can try to sort of see if I'm on the right track. So one they gave is 33 and 21. This is supposed to be equal to 80. Sorry, not 33 and 21. They give 30 and 21, and that's equal to 80. Okay, so the code is working for that one. Another example they give is 102 and 33, and this should be equal to 333. There we go. Okay. Now the next example they give is, the value of n is 100,000 or something like that. And the way I've written this code, it's way too inefficient because I'm actually constructing every single tree up to whatever value of n I need. And so the number of, the memory and the number of computations that need to be done is just too large. Or at least, I tried to run it for a little while and the code never finished. The actual question on Project Euler wants the function to be computed for extremely large values of n and k. So we can see the original problem statement here, and it's asking to compute f for n equal 10 to the 17 and k equal 9 to the 17. So by constructing the trees from the ground up, no computer in the world would ever be able to do this. So there's something that I did again in the code to. I was just curious. I thought I had an idea, and I'm like, let's look for a pattern in something else. So here's what I do. If I use these two trees as an example, let's fix a particular number. Let's say, let's fix the number 6, okay? So from T7 onward, 6 is always going to have a parent. And I want to know what is that sequence of parents for the number 6 going to be equal to. So in the tree T6, 6 is the root. It does not have a parent. In the tree T7, the parent of 6 will be 7. We see here that in T9, the parent of 6 is 8. And here in T10, the parent of 6 is 10. So I wrote some code to also compute the sequence of parents for a fixed number. So what I'm going to do here is I'm going to write these out for the number 6. And we can see that there's definitely a pattern. Let me write this again. Okay, so the first parent is 7. Then so this number corresponds to the tree T7 because that is the first tree when the number 6 has a parent. In T8, the parent of 6 is 8. In T9, the parent of 6 is 8. In T10, it goes up to 10. So once I tell you what the pattern is here, it's going to be obvious. There's 1 7, then 2 8s, then 4 10s, then there are 8 14s, then there are 16 22s, and then, well, I haven't counted them, but I bet you there are 32 38s, okay? So a single number has the same parent for, the number of trees that it has the same parent for is a power of 2. And not only that, the parents increase by powers of 2. So for example, if I subtract 6 from this, we see now that these numbers are all powers of 2. 1, 2, 4, 8, 16, 32, and so on. Okay? So what this says is if I have a fixed number, in this case 6, I should be able to abuse this pattern to find out what the parent of 6 is for any value of n. And that should be very quick. It's just going to be, there's going to be logarithms base 2 involved in exponentials or 2 to the power of something, and it'll be very quick, okay? So if for any value of n and k, I can find, so if I say I'm in tree n, Tn, and I have an arbitrary value of k, using this pattern, I should be able to find the parent of k very quickly. And then once I have that parent, I should be able to use the same technique to find the parent of that node very quickly. And I'm just going to do this over and over to go all the way up the tree. And if I keep track of all these parents and add them all up, that's going to give me the function f and k. So I'm going to try and implement that here. It'll be somewhat numerical, I suppose. But what the first thing I'm going to do is I'm going to verify the final example that was given to me by the user and make sure that the output is correct. And then I'm going to try and evaluate it for this quantity as well. And I'll submit my answer and hopefully get confirmation from Project Euler itself that, that my answer is correct. Okay, but I still have to think a little bit about, exactly what the relation between n and k and the parents and this pattern of powers of 2 is. I should also say I haven't actually proven that this pattern continues for all values of n and k, but I mean, it's pretty striking. I have checked it on my own for various values of n and k, right? So if I look at the number 34 and its sequence of parents, I start with 35, then it goes up by 1 and stays like that for 2. Then it goes up by 2 and stays like that for 4. Then it goes up by 4 and stays like that for 8. Yeah, I haven't proven it, but I'm just going to assume that this does continue forever. And let's see what we can do. Okay, so really what I need to be able to do, the one thing I really need to be able to do is for a fixed value of n, if I take a value of k, I need to be able to compute the parent of k very quickly. And if I can do that for an arbitrary value of k, then I can just keep computing parents of parents of parents of parents and so on and add those all up. And that'll give me the function f. So what I'm going to do is I will denote p sub n of k is the parent of k in Tn. Okay. Now, in my array structure convention, let's fix n for a moment. So I have a sequence of numbers that looks like this. And they're sort of grouped into things like this. Okay. So the number, let's fix, oh, sorry, this is not for fixed n. This is for a fixed value of k. I have an array. This number, the index, corresponds here to k plus 1, and then k plus 2, k plus 3, k plus 4, and so on. And that's because for a given value of k, the first tree in which it has a parent is k plus 1. And this number, the actual entry here, is also k plus 1. So I can write p of k plus 1k is equal to k plus 1. So this is saying in the tree tk plus 1, the parent of k is the root itself, k plus 1. Okay. So what I want to do is do I want to do exactly? What I need to do is I need to figure out, like, I know that these elements are the same, those elements are the same, those elements are the same. So I need to figure out which of these buckets I fall into. And that's going to depend on the value of n minus k. Okay, if n minus k is equal to 1, then I'm in this bucket. If n minus k is equal to 2 or 3, I'm in this bucket. If n minus k is equal to 4 or higher, I'm in this bucket. So I think what I need to do is I need to take a log base 2, and do I round up or round down? So if I round that up, I think that's correct. So this tells me which bucket I'm in. If n is equal to k plus 1, oh wait, no. I need to round down and then add 1. If n is equal to k plus 1, then that's 0, and I add 1, so I'm in the first bucket. If n is equal to k plus 2, now let's say n is equal to k plus 3. So this is 3. Log base 2 of 3 rounded down gives me 1 plus 1. So I'm in the second bucket. But I think what I want to do is I'm just going to take this instead. I'm going to raise, so 2 to the power of that plus, I think this here, I think this is PNK. I'll probably verify this numerically for several values of n and k to convince myself, but it seems to make sense. If n is equal to k plus 12, that puts us into that bucket for sure. N is equal to k plus 12. So then this number here would simply be 12. Base 2 log of 12 is between 3 and 4, so that becomes a 3. 2 to 3 is 8. 8 plus k. So add 1, add 2, add 4. Maybe it's plus k minus 1. It might be plus k minus 1. Okay, but let me just type this in for a few values of n and k, and see, and I'll compare it to my the arrays that I have, and see if I get the right answer. Okay, so I'm not getting exactly the answer I expected. Let's look in more detail. Let's just look for the number. Let's look at the number 5. I don't really need this many values of n. Let's lower n to 32. It's power of 2. Okay. So as a function of n, p and k goes like this. So I'm looking at node 5. Let's say for n equals 6, right? The very first value should be 6. Okay, so the log base 2 of n equals k. So that's 1, so that whole thing is 0. I have 2 to the power of 0 is 1. Plus k minus 1 gives me 5. So maybe I don't need that minus 1. Okay. What happens if I change, if I increase this by 1? 7. So they're off by 1. Let's increase it to 8. They're again off by 1. Increase to 9. They're again off by 1. So yeah, maybe this minus 1 doesn't have to be here. Let's try 10. Okay, so now they're the same because I've changed the code, so it seems to be working. 11, they're the same. 12, same. 13. Okay, yeah, so it seems to be working now. So let's try this now for a large value of n, relatively large. So one of the examples given by the viewer was n equal 102 and k equal 33. So I'm going to write a new function. Maybe I should call this parent p, like that. So it's just computing the parent for a given value of n and k. So if I compute now p of 102 and 33, parent 102, 33 gives me 97. Now I want the parent of 97, and it's 101. Now I want the parent of 101, which is 102, right? We know that. Okay, so now 33 plus 97 plus 101 plus 102 is 333, which is the correct answer. All right, so I should be able to write something really quickly now that computes this function f for values of n and k. Okay, so what we're going to do is we're going to start at k. We'll have a running total, which in fact is also started at k. And then while the index is not equal to n, we add the parent of the current index to the running total. And then we change the new index to be the new parent. So we're just kind of moving up the tree. Is this the wrong syntax here? I guess so, yeah. And then I suppose I need to add, no, I don't need to add the last parent. This should be, that should be it. So now, with a couple of values given to me, let's check that this gives the right output. 333, great. Now I'm going to check the value of the larger example given by the viewer, which I was not able to check before. Okay, so the number for n is 139930, and for k is 497. Output here is 831496, which is what I was given. So now let's see if my code will work for the values given in the values asked for in the actual Project Euler problem. I hope I don't run into some kind of numerical overflow stuff here, rounding errors, that kind of thing. If this outputs an integer, then I'm fairly confident. I'll be fairly confident in. Well, it'll almost certainly output an integer because I have a whole bunch of rounding going on in my code. Well, let's just see what happens. Oh, gosh darn it. I can't write that into Project Euler now, can I? Okay. So the way Project Euler works, you're given these problems and every single answer is an integer. But apparently in this case, it's an integer that's 18 digits long. So I might, I wrote some code a long time ago to have fun with Project Euler that does addition of arbitrarily large integers. I might need to implement that. But then this part of the code might be an issue. Will it? Let's compute the parent of this first node, 9 to the power of 17. Oh my. Okay, do I want to spend time adapting my other code to this problem? I've come this far. I may as well try and adapt this other code that I have to this, but I'm not going to do that part live while recording. I'm going to spend a little bit of time taking the code that allows me to add arbitrarily large integers together and figure this out. Okay, so I'll stop recording now. Hopefully I'll come back within the next short amount of time. Okay, minor change of plans. Rather than adapting all of my previously written code for large integers and stuff like that, one function that I wrote a long time ago to handle this kind of thing is essentially to display these very long integers that are stored in memory. And I think I can just call that function because I'm pretty confident that MATLAB here is doing the correct computations with numbers that are 17, 18, 19 digits long. It's just not displaying all of them. So they are in the memory. I don't think that the rounding off of the logarithm that I use will be an issue, but I'm going to try and do this and input the answer into Project Euler and see what happens. I also realized in the few minutes that I was offline that it might be easier, or I wouldn't have to worry so much about rounding and so on if everything were just done in base 2. Computing a base 2 logarithm when the number is written in base 2 is a lot easier. You're just looking at the length of the number, or the number of digits in the number, and computing 2 to the power of something when everything's done in base 2 is pretty simple. You just add a 0 to the binary representation. I'm not going to go into all the details here. I just kind of want to make sure that what I'm doing here is the right approach. Okay, so first we had this output for the actual function itself. And what I'm going to do is give this array of numbers here. So this array represents this number, but written backwards. So we see 24031, 24031. So if I reverse the order of that array, hopefully I can just copy this and paste it into the Project Euler submission box. No, it didn't quite pick everything up there, so I'll just have to type them in one by one. It's fine with me. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18. Okay, so it's the right order of magnitude. And let's see if this is correct. No. Ha. Um, 831496. So it works for that. It works for this example that was given to me by the viewer. Maybe there is a rounding off error in the code that I wrote, or something significant happens. Sheesh. Yeah, I mean, I'm sure this video is probably approaching an hour long at this point. So I think, I mean, I'm confident I have the right approach in how to solve this problem. I just don't want to have to spend the time writing all this stuff for arbitrarily large binary numbers and so on. Yeah, maybe there's like a really quick way of implementing this expression. If there's a really quick way of evaluating that for large values of n and k, then sure. I can't think of what it is right now, and I don't think I finished the interesting part of the problem as far as I'm concerned. Yeah, overall, the key here, for me at least, was recognizing this structure between child and parent in these trees. You know, maybe this is of course something that I did not prove. I'm relying on the fact that this is true for all values of n and k, but the pattern seems to hold for really large values, so that's not a guarantee, but I don't think that would be the issue. And I was really lucky to see this. It was, as far as I'm concerned, more or less a total fluke. I just wondered what would happen if I plotted or if I computed the parent of a single value as the tree gets bigger. And I saw this pattern come out, and then it became pretty clear how I would solve this. Yeah, these project order problems can get very, very difficult, and they're typically not the kind of thing that I am an expert in at all. So, you know, I chalk this one up very much to luck that I saw this pattern, because it was just a random idea that I had to explore. Yeah, I'm going to end this one here. You can let me know what you think. Don't know how much time I would be willing to spend on a project order problem in the future. I mean, I've done a lot of them on my own, but for the purposes of making a video on this channel, you know, so much of the work has to be done offline, and so much of the, you know, the videos end up being extremely long. So I don't know how, you know, how feasible it would be to do many of these in the future. But I'm always interested to hear what the sort of alternate approach to think of these project order problems is to make the computations feasible. Thanks for the submission, and thanks for watching.